just to know, as you have just heard. So now we can start. Thank you very much. I'm going to share with the presentation that we have prepared for this. Okay. I don't want to ask if everyone sees my presentation. I will assume that everyone does. And again, thank you very much for being here today. Here is a seminar series of Glow Bias. My name is Katerina. I'm a postdoctoral researcher, and I'm going to be the chair for today's session. I'm part of the training and education group of Glow Bias. I participate as a volunteer for the people hearing this today and interested in bioimage analysis. Being a volunteer in Glow Bias is super nice, and I encourage you to look for it and how to do it. So today we're going to have a session on image analysis, on doing bioimage analysis with using Galaxy. And for this, we have different presenters. We have Beatriz Serrano, Leonid, Ricardo, and Anne. And I will let them present themselves because we have a lot of speakers today. I don't want to make it very long. I want to let them speak all what they have to. So, yeah. Globias has more than 50 volunteers. We are a lot of people volunteering for this and interested in this. And there are one community manager and 12 steering committee members. It's a nonprofit association since last October. And it's creating a sustainable base and legal entity for many things. But the main objective and the main goal of this is bioimage analysis, developing training materials, do activities, workshops, consolidating standards. There are many, many things, many subgroups, and many people doing great stuff, which is really, really great. It's supported by a Chan Zuckerberg initiative and hosted by German Bioimaging. So seminar series are a set of webinars, seminars that we host online. And the idea is that there is a topic, and this topic will have several sessions on it, and we will invite people who have something interesting to say about bioimage analysis, something more practical for intermediate and advanced people. And yeah, we do a seminar series every month. So stay tuned and join the next ones too. Also, thanks to the Broad Institute for providing help with the infrastructure. And again, remember that this session is being recorded. Now, what we have upcoming is the third round of the Global Bias seminars, which is current and future plans for essential bioimage analysis tools. And the next talk that we will have will be on QPath by Pete Bankhead. And please scan the QR code, join, check everything, visit the website. You will find all relevant information there. And I think that's everything that I had to tell you. Yes, thank you for attending, and please enjoy everything. And thank you for being here also to the speakers today.
Thank you, Katerina. Shall I start?
Yes, please.
Yeah, thank you. Okay, so I'm going to share my screen. Let's see if I manage with so many problems that I had with the connection today, but I should. And you should be able to see it. And now I even see you on a different screen. Is it everything okay?
Yes, thank you.
Okay, great. Yeah, so we are today 4 speakers. They will introduce themselves when they are speaking. I will just introduce myself now. My name is Beatriz Serrano-Solano. I work at Bioimaging in the BioHub in Heidelberg. And I also work in the project that you may know, and there's a webinar tomorrow, Global webinar tomorrow as well. This is AI for Life. So today we are going to talk about image analysis using Galaxy. I will do the introduction and the closing of the webinar, and then Leonid, Anne, and Ricardo will cover different demos on different aspects. So the first thing that we need to start this webinar is to define what Galaxy is. So you may have heard of it in different disciplines as well. So Galaxy is a data analysis platform that it's open source, so you can anytime take the code and also contribute to it. It's web-based, that means you don't need to install anything, you don't need dependencies or any other of these things, you just need your browsers to do this analysis, and it's accessible for everybody, so there's no not only open source, but also open infrastructure that you can use for free, and you only need to create an account in a server. And it enables you to create analyses that are reproducible and transparent, that you can share with others, that you can attach to your papers and so on. There is an URL there in the slide. There is galaxyproject.org, and that's the Galaxy Community Hub. There you can find plenty of information about, for example, the communities that are geographically organized, or by topics, or training pointers to training materials, all the organization about the project, and all the information is on the website. Now, this is the information about the project that is, by the way, now 20 years old, and there are different servers. So that's how you can really use it. And these Galaxy servers are distributed across the globe. There are more than 160 that we know of, but it's a bit hard to track because, for example, the local installations, this is very difficult to know. There are some that are in institutes, there are in companies and so on. You will find all the list of the ones that are tracked at least in this URL that you see at the bottom of the slide. That is galaxyproject.org/use. And there are three main big ones in three different continents that are public and with a powerful infrastructure behind. And this is the one in the US, use galaxy.org. There is another one in Australia, use galaxy.org.au. And then there's the European one, use galaxy.eu. So here in this presentation, we are all the speakers based in Europe. So we will talk about the European one, and you will see demos on the European one, but also in local ones. So depending on where you are located, you can go to this URL and check the one that is better for you. Also important here is that Galaxy has a kind of an app store that it's common for all the tools that are available for the different servers. And each one of the admins of the servers, they are responsible for having these tools installed there. So it might be that there are some tools that are in one server and not in the other. So in that case, you can contact your admin and ask them to install that particular tool that you may need. So that's on the general global infrastructure. Now, if we go a bit closer into how is this web-based interface, that by the way, it's web-based, but it's also you can also access this programmatically if you want with an API. And here we are going to focus on this basic interface. There are many details on this, but we just go very broad on it. And the first thing that you may notice is that the screenshots that I had before were on the big Galaxy servers, and this is a bit different. It has some colors on the masthead. It's a bit different. It says Galaxy imaging. So this is important because it's still the same infrastructure as the European Galaxy server. That's where we are doing this. So the URL is imaging.usegalaxy.eu. Is the same computational resources, is the same quota, is the same memory that you have available. You have the same resources behind. It's just that the front end has the tools filter, because there are in this app store, there are now like 10,000 tools. There's no point in having all of them there. So we just filter and go the ones that are relevant for the imaging community. So that's why you will see. Okay, so let's go step by step. So there's the tools. Once we have the tools selected here, one can see a panel here with all the different tools. You can search for them, but we already pre-filter the ones that might be relevant for imaging. Then we have a central panel in which all the information is explained. So whenever you're going to run a workflow, use a tool, or anything that it's changing, is going to happen in the central panel. In this case, this is the entry page. So we have a basic summary of the training and so on. So there is just basic information now, but this will change whenever you use it. And then there is on the right side, there is a history. And that's a very interesting and powerful side of it, because everything that you do gets tracked there. That means that you can see it as a kind of an electronic lab notebook in which you write everything that you do so that you next time can repeat the experiment. This is a similar concept. So in that case, every tool, everything that you are doing, it's tracked there. And you will see the status of the things that you are running also on that right panel. So that's the history, that's the whole interface, but you see now that on the very left side, you have upload, tools, workflows. So we will cover some of them now. In terms of tools, there are plenty of things. You could see many logos here that you may recognize. And these are classified on data in and out, data management, data conversion. There are plenty of image processing, image analysis, and then also the visualization. And again, this is all on your browser, so you don't need to get out of this or install anything special for this. That's all in the browser. And this is interesting as well, because in the same workflow, being this workflow as a session of different tools that are chained, this will enable that you use your favorite tool for the particular task that you're interested in. So maybe you want to do, I don't know, we want to use something, some model in cell pose, then you do it. And then maybe you like analyzing the features with cell profiling. So you can change these things together. And in the end, you have a workflow that it's fully reproducible that you can share with others. So today we're going to see in demo one by Leonid. He will do some transformation, image conversion. He will use a SciPy and scikit image. Then Anne will come and do the same, but instead of using regular Galaxy tools in automated workflow, she will do it through a notebook. And then we'll have Ricardo that will cover more the data aspect using Homero to get data in and out, and also visualization of OMSR using BizR inside Galaxy. So these are the tools, these are the tasks that are derived from these different tools. I guess you are already familiar with many of these that we show already, but basically it covers all the different aspects of the life cycle, from getting the data to doing something with it, to do some image pre-processing if you need to do the image analysis, segmentation, registration, tracking, feature extraction, all these things. And then you can inspect the data visually at any time. It doesn't have to be at the end. So every time you do an activity, you will see that in the history, and then at any time you can go and visualize something to see what happened there. And if you like it, or you need to run something in particular. We also have incorporated recently the bioimage.io model. So basically there is a tool that can retrieve the models from bioimage.io and run these AI models as well there. And they're also covering other communities that are related somehow, like the spatial omics community. So that's more or less an overview. I know there is a lot of information here, but that's more or less an overview of the things that you can do right now. Now, when you have a tool and you want to run something, you will see something like this. So we go to the tools panel, and in this case, for example, I wanted to do something on cell pose. So I type here cell pose, and then this appears. So we can now select the tool that we want. Once we click on the tool, there's a central panel change. So now it appears all the parameters that cell pose is expecting from us. You see, it's an all graphical user interface. You don't need to write any command or anything like this. And once you've completed everything, you run the tool with the button at the bottom. And then on the right side on the history, there will be a new box that will appear saying, okay, there is a task here that is running. And this task will be at the beginning yellow while it's scheduled, and it can actually run or running. And then when everything is good and it worked well, it becomes green. If something failed, it becomes red. And then you can go and check what was wrong and why it failed. So that's when you have a tool and you want to run it, that's very straightforward. Now, if the process that you want to run, it's more complicated, you may need a workflow and you may need to put several of these things together. So in this case, you have an example of a workflow preview. It's a very linear one. It's a simple one as well. So it's not every one of the boxes is a tool, but you can make this as complicated as possible. You can have like several branches data coming from different sources. I mean, you can be as creative as you like. For now, we have this very simple one with boxes that are connecting to each other, and the outcomes of one tool are used as input as the next one, and this is all graphically represented. I would like now that you take a look at the right side of the panel here, because there are also interesting information here regarding metadata. So you have, for example, 3 buttons to download this workflow, so you can do whatever you want with it. You can share it or do as you like. You can edit and change some tools and maybe are not exactly what you want this workflow to do, and then you can run it as well. And then you have about this workflow, and this particular workflow, I didn't create that one, I uploaded. So someone else created this workflow, shared it with me, I imported it, and I have it now as part of my set of workflows. You see also that there are some tags, so you can put some labels there to say, okay, this is a cell profiler workflow, this is an imaging one, and also interesting that you can share, and you can share with different groups of people. So you can share only with one person. If, for example, you are collaborating with someone and you only want that person for now to look at the workflow and share with him. And then the other one would be sharing with everybody. So let's say your workflow is now ready for production, everyone could use it, and you want to share it or put it next to your publication, then you can share with everybody. And we will see this now here. So the workflow section, you have all these different workflows that you created or you imported, but they are somehow linked to your user. So this is in the section My Workflows. Then you have the ones that people share with you, and then you have the public ones. Now, there's a new section from, I think, last year or so, that is the workflow invocation. And that's very interesting as well, because this keeps track of everything that you were running a workflow. And you see now that the boxes there that are representing it have a green header. And that means that the workflow went very well, that things were nice, and everything was as expected. Now, if when you are doing this, you can see that some of them are red, for example, that means that it failed this particular tool. So you can go now and see in this part of the process where the problem is and fix it, or maybe replace it with something else, or maybe that tool shouldn't be there, or the input is wrong. There can be many different causes. So that's keeping track of all the different invocations that you did. And yeah, you can retrieve everything that you did in the past as well. There are more interesting things. I just showed the overview right now of the workflow invocations, but there are also interesting features for sharing in a different way as well. So that's exporting. So you can export as an arrow crate. This is a fair digital object that contains a lot of metadata and that makes your workflow really more enriched. You can also share with biocompute object, or you can just get a zip file, kind of compressed file with all the information that you need. Final tab that I want to highlight regarding the workflow invocations is the metrics. And I think that's interesting to know, and that is important that we are all aware that the tools that we are using and everything that we are consuming here, even though it's for free and there are plenty of infrastructure there, it has a cost. And it has a cost in computation and in memory. And it's not only an economic cost, but it's also a cost for our planet. So that's also something that we should be paying attention as well. Finally, a different thing. This is like kind of a different concept. This is an interactive tool. So basically, this is a way for you to reproduce what you could have in a kind of a desktop environment. So you have here virtual desktop. You have kind of notebooks like Jupyter, R, and so on. So many of them might be familiar to you. And you access to these ones in a different URL. This is live.usegalaxy.eu. And this is something that Anne will cover in demo 2. So I will not say much more about this one. But the functioning, it's a bit similar. So you click on the tool, something starts, and then you can start typing your code if this is what you want. Finally, I want to highlight a couple of things on training. So the first one is that there is a fantastic repository that is called the Galaxy Training Network. It's a collection of tutorials, and you have also slides, you have sometimes recordings, all the workflows that are attached to them, all the data sets and everything. It's collected there, and it's classified into different categories. So the screenshot here is the one that is available for imaging. We have at the moment 7 tutorials. We have some others that are cooking and will be released soon. And this is very interesting resource because you go step by step in each one of the each one of the tutorials, and you can see which tools were used, which parameters. You can also have questions. It's also very, very easy to contribute here. So anyone can create a tutorial, and the workflows are also shared in the workflow hub, which is also a good thing. So that's on the Galaxy Training Network. And today, the 2 ones that are involved will be covered by Leonid and Ricardo. So you will see in practice how this is looking. Finally, for trainers, this is also a very interesting resource. So there is a training infrastructure as a service. And this is something that trainers can request. So basically, if you're going to give a training and you have, for example, 20 students that are coming, and you don't want them to be waiting in a general public server in the queue, just can be other people using the resources, you may need to wait a bit, and you don't want that. So in that case, there is a special queue that is created for your particular training. So basically, you as a trainer, you say how many people you are waiting, you're expecting to have in your workshop, which tools or workflows you're going to use to see the consumption that is needed, and then you have some machines that are reserved for you. That means that everything will run very smoothly while you are delivering the training, and you will get a special link for the trainers to join, and that will enable also you to track how things are going. So where are the different trainees, where if they are stuck, if they have a problem at some point, if there are some tools that are blocking them. So you will see in an anonymized panel how these different people are doing in the training without the need to be asking constantly how they are doing. That's all on the training aspect. Now we go for the demos. So first one would be Leonid with the Galaxy workflows. Then we have Anne with the Galaxy notebooks, and then we will have Ricardo with the data management. Then I will come back with some summary at the end, but for now I will hand over to Leonid.
Yes, thank you, Bea. Let me share my screen. So I think you should be able to see my browser window now. So what I will show you is how to perform an analysis of which involves image segmentation and object counting using an example fluorescence microscopy image. And I will do so by loosely following a tutorial that is also available on the Galaxy Training Network. That is Introduction to Image Analysis using Galaxy, as we already mentioned before. And yeah, without too much text, I want to directly dive into it. So what we are concerned here with is an image that has DAPI-stained HeLa nuclei. We will see how it looks in a moment. But to start with, I want to mention that I'll be using a local Galaxy instance. This is for the simple reason that using a local instance reduces the waiting time that one has to wait basically when you use a public instance before a job starts, a job that you submit, a task that you submit, a tool that you execute. But if you want to reproduce the steps that I take here, it's perfectly fine to use a public instance like use galaxy.eu, for example. Yep. So that said, the first step of the procedure will be that I acquire the data that I want to work with. And to do so, I pick the URL from the tutorial, which is linked to a Zenodo, to a zip archive that is hosted on Zenodo. And to load this into Galaxy, I will use the upload button. Then there's a paste or fetch data button, and there I paste the link that I just copied. From my experience, it is helpful to specify the file type of the file that the link points to in case that you know it. And we can also adjust the file name based on the link that we just pasted here. After we have done that, we just hit the start button and then the close button. And then we see that the job is submitted and is being executed. This is indicated by the orange color of the job here. So orange means that it's running and green means that it has finished. So this here is our downloaded zip archive now. By downloaded, I mean it's downloaded into our Galaxy history. And the first step now will be to actually extract data from this archive. And to do so, I will use the unzip tool. So I click on tools, and then in the search box, I just write unzip, and there we will find a tool that is called unzip a file. And since we only have one single item in our history, the input file is already pre-selected correctly. However, we only want to extract a single file from this archive. And to do so, we simply copy the name of the file from the tutorial into this input field here. And finally, we hit the Run Tool button. And then the story basically repeats. It turns, so when the task is gray, this means that it is queued. When it is orange, it means it's being executed, and green means, yep, it is done. So now we have this file, this image unzipped. And what we want to do then is to rename the item here in our history so we can easily identify it later on. We will just name it our input.tif file because we will use it as an input for our analysis. By the way, by clicking on the I symbol here, I can visually inspect the image. And as you can see, it's hard to see what is actually contained in the image. So it's hard to see the cell nuclei here. This is due to the fact that the contrast of the image is just not that good. And this is why we will also improve the image contrast later on. But first, let's see how we can inspect the metadata of this image. And to do so, I use the show image info tool, which is a wrapper for a bioformats tool. And here I select the image that I want to inspect, and then I run the tool. And this will give me an output that looks like this. So what we can see here is, for example, the width of the image, the height of the image. We can see that it is a grayscale image. And I think there's also the number of bits per pixel in the color channel. So it's a 16-bit image. And this is also the reason probably why the contrast of the image is so bad, because the range of possible values is quite large. And so it's not an 8-bit image, but a 16-bit image. And our next step will be to perform a equalization of the image histogram so that the cell nuclei hopefully become better distinguishable. To this end, we use a tool which is called perform histogram equalization. We select the input image and leave everything else on default. And after running the tool, you will see that the cell nuclei are much more easy to perceive now. Okay. So when it comes to the analysis, so remember, we want to do image segmentation. First, we want to do some pre-processing. And by pre-processing, I mean we want to do some very rough noise suppression. And this is most easily done using a filtering tool, for which we use the filter to the image tool. This is wrapped around SciPy. We choose the original input image as the input image of the tool, because we want to have as much information in the image available as possible, so the full 16 bits, and leave everything else on default. And when the tool has finished running, we can compare it to the original input image. And I hope that you can see that it indeed looks kind of smooth, even though the contrast is not that good. I will rename that history item, that file, to input_smoothed, so we can identify it more easily later on. Then I will repeat the histogram equalization operation on that smoothed image, so we can more easily see what is going on in the image. So by comparing this normalized and smoothed image to the just normalized image, which hasn't been smoothed, it's easily seen that this image is much more blurry, which is basically a side effect of the noise suppression. Okay, and I will name that item, that history item, input_smoothed_normalized. Okay. And I think I should also rename this one here to just input_normalized. Yes. Okay, now for the actual segmentation. For the segmentation, we will use a thresholding method, which is available in the threshold image tool. This is this one, and the method that we will use is simply Otsu thresholding, which is a widely used, widely established, although quite old method, but one that is very easy, very fast, and still very useful today. And I select the smoothed image as the input, and then I hit the Run Tool button. And this is what the result image looks like. So here we have black image pixels, which correspond to the image background, and white image pixels, which correspond to the image foreground. However, we also want to perform object counting and not just segmentation. And this means that we need to identify the individual objects and not just the image foreground. So one further step that we need to perform is to convert that binary image, binary in terms of black and white, into a labeled image or label map, which means that we will have an individual value, an individual label for each object, for each segmented object. Okay, so we choose, let me rename it first. What is the suggested name here? Yeah, it's input segmented. I rename the segmentation result to input segmented, and then I run the conversion tool, which will convert the segmented image into a label map. And we will do that by using connected component analysis. And you will see in a moment what the resulting image looks like. So this is the result. It looks almost entirely black, which is due to the fact that the labels which are assigned to the individual objects are numbered consecutively. So the first object is numbered with a value, with a label 1, the second one with a label 2, and so on. And since we have n labels, and n is much smaller than 65,000, since we have a 16-bit image, by n I mean the number of objects, the entire image looks black, but it isn't, as we will see after performing another histogram equalization on the result of the conversion. It's still running, but we can already see it. Okay, so yeah, this is the result. Here it is. It can be seen much more easily that the objects are numbered with individual values, individual labels. Okay. So I will again rename this item here. This was the result of our conversion tool to input underscore segmented underscore labeled. And then I will create an overlay of the segmentation result in the input image. To this end, I will use the overlay image tool. And I will use the original input image, which was normalized as the intensity image, and the label map, as our segmentation result, basically. And then I want also to include the numbers, the values of the labels into the overlay. Okay, so this is what the segmentation overlay looks like. As you can see, we have segmentation contours for all the segmented objects, and we have the actual, basically the numbers of the objects annotated right next to them. So the final step of the analysis that we will run here is to perform object counting using the count objects tool. We select the label map as the input and run the tool. This should give us the number of objects in the image that have been segmented. This is supposed to be 425. And by looking at that image again, we can see, yes, indeed, the object which is labeled with a value of 425 can be seen down here. And I think you won't be able to find any object with a value with a label higher than that. Okay, so this has been the procedure for the interactive, basically for an interactive analysis that I have performed. Now I want to create a reproducible workflow out of this analysis. To do so, I can use functionality inside Galaxy, which greatly simplifies the creation of the workflow. Namely, I can directly extract the workflow from the history that I have created. Okay, so I use this extract workflow functionality. Here I have to deselect the tools that I don't want to be included in my workflow, like the unzip tool. Let's say I want to have this workflow to only perform the segmentation and only create the segmentation overlay. This means I won't need the show image info tool. I won't need any histogram equalization tools besides of the first one. And I won't need the count objects tool. Besides, I don't want the whole zip archive to be treated as an input. Then I click the create workflow button, and then I want to edit the workflow. Okay, this is what it looks like. Let's drag the steps a bit apart from each other, so it's more easy to see what is actually going on. This here is supposed to be the first analysis step, the filtering. And what I have to add here is the actual input of the workflow. To do so, I click on inputs and then on input dataset. I mean, dataset may be a bit confusing because it's just a single input image, but yes, this is how it is called a galaxy. So it's an input dataset. And then I connect the output of this input, which is the image itself, to the input of the filtering tool. And in addition, I need to connect the output of the input to the histogram equalization. Okay, so this is what will be going on in this workflow. This is what it will look like. One final thing that I need to do is to select the output of the workflow by clicking this checkbox here. So the overlay image is now marked as the output of the workflow. Then I want to name this workflow image segmentation. And then I think I can save and exit this workflow. Okay. Now I want to show you how this workflow runs. To do so, I click the Run Workflow button. And for the input, I will use just the same input that I have also used in my manual analysis. Then I click the Run Workflow button. And then you can see how the steps are being processed one after another. They first turn orange, then they turn green when the computations are finished. And the image that I will receive from the execution of this workflow should look the same as the image that I have produced using my manual analysis. Yep, this is what it looks like. We still have this object labeled 425 at the lower bottom. So yep, it looks pretty much the same. Now I want to extend the workflow so I will be able to run the analysis not just on one single image, but on a whole collection of images, like all images from the zip file that I had downloaded before. And to do so, I will first create a new workflow. And in this workflow, I will embed the workflow that I had just created before for the analysis of a single image. And in this workflow here, which is supposed to perform the analysis on a collection of images, I again need to add an input, but this time not just for a single input dataset, but for a dataset collection. And again, I need to connect this input to the input of the segmentation, image segmentation workflow. And finally, I will mark the output of this embedded workflow here as the output of my wrapping workflow for the whole collection of images. Okay, I will name this workflow segmentation of collection of images. And then I create a new history, which I will name demo part 2. And then I go back to my previous history and I will copy the downloaded file, the zip file from my current history to the new history that I just created. Now I'm a bit confused. Why didn't it change its name? Apparently I didn't save it or something. Okay, I think it should be this one. Let's try. Yes, this was right. Okay, so now I have the zip file copied over to my new history. I'll rename it again, demo part 2, save, okay. And now I will run the workflow. No. First I need to unzip the file. For this, I will again use the unzip tool. I will run it with this zip file that I just copied over, but this time I will perform the extraction of all files in the zip archive. So this gives me a collection which consists of 9 datasets. Datasets means 9 images. And then I can run the workflow that I just created. This was this here, segmentation of collection of images. Let's run this on the result of the unzip operation. Yeah. And here we can again follow how the individual tasks of the individual steps of the segmentation workflow are queued and executed consecutively, one after another. So they turn from gray to orange to green. And at the final stage, you will have a collection of 9 segmented images. Let's wait for this. Okay. By clicking on this item in history, I can see each individual object inside this collection, and then I can inspect it. So we see that we have different segmentation overlays for the different input images here. Most of them look very useful, very usable for further analysis. So the segmentation performance seems to have been quite good. For some of the images, segmentation results are not as good. This is related to the distribution of the intensities inside the images. So Otsu thresholding assumes that the distribution of intensities is bimodal. For these images, it seems to be not bimodal. This is why Otsu thresholding performs not so good for several images. Yeah, but for most of the images, it has performed sufficiently good, I think. That's it for my demo part. I think we can do the questions later on. Thanks.
Okay, so I think now it's my turn, and I will follow up on what you did, Leonid. So let me share my screen first. Hopefully, should work now. I'm moving this. And as Bea mentioned before, we will start from the live usegalaxy.eu. So now we will go to interactive tools. So what Leonid showed is very interesting when you want to automate a big data processing chain for your image analysis. But there are many times where we want to interact, either to check a specific image, or we want to develop a new algorithm, or we want to change something at a new step. And it's very common to use interactive tools instead of having already develop a new tool in Galaxy. That's usually how I do it. So I try to use as much as possible for production this Galaxy tools, the standard Galaxy tools showed by Leonid. But when I want to do more interactive work, I use this live.usegalaxy.eu, where you also need to be logged in to be able to access. And then I can access different tools, which you can see here. And the one I will be using is Jupyter Lab. And I will start it. So just to make sure you understand the tools for interactive tools are very similar to any other tools. You can also access them through this tool box here. If I type Jupyter, I will have different interactive tools. And this live.usegalaxy.eu is the same infrastructure as mentioned by Bea, but this is like a shortcut. So if I click on this Jupyter tool here, I will have exactly the same setting as any standard tool. and I can start like the Jupyter Lab as a fresh notebook, or if I had a Jupyter notebook already in my history, I could load the previous one. So I can load the previous one. So we will start from a fresh one. So you can click on Run here. And as you can see here, it's gray. And when it's gray, it means it is not started yet. It's in queue. And because it takes a bit of time for interactive tools, I will use a one I have already. But normally, when you have launched an interactive tool, you have these interactive tools here. And when you click on it, you can see what is running. And of course, you see some of the tools I have already started before, because I'm working quite regularly on Galaxy. And we will use one that is already running. So when it's running, it's in orange and it's spinning. And it doesn't go green because it's interactive tool. So it's running until the end of the life of the interactive tool. So I don't remember how long it stays running for this Jupyter Lab, but it's like 1 or 2 days, and then it will stop automatically. So it's really for interactive work, so make sure you save everything. So then once it is running, like here, spinning, you can click here on your Jupyter tool, interactive tool, and it will start a Jupyter Lab. So if you are familiar with the environment, Jupyter environment, it's very classical. And here you have different folders, which is the output if you want to communicate back to the Galaxy. And the way I work normally is I try to, especially when I want to develop, for instance, a new tool or a new algorithm, I have a GitHub repository where I will develop my new tool. And then I copy back and forth between my GitHub repository and this Jupyter Lab instance, so I don't lose anything. So it's here, for instance, I can clone a GitHub repository where I have prepared some Jupyter notebook for the demo. And I guess we can also paste it somewhere in the chat for people to look at it later on. Then I will clone it. So I do a git clone. And I see my new repository. So here, everything I have done on maybe on a previous Jupyter Lab, or maybe even locally on either Galaxy instance or any Jupyter Lab, I can reuse here. In this folder, I prepared 2 Jupyter notebook, but I will show only one. And you have also the rendered version here. If you click here, you can follow the Jupyter notebook without having to execute it. So let's open it, and it's like any Jupyter notebook, you can double click and you will have Jupyter notebook with some metadata here. Sorry, and I can remove it. And of course, when we start the Jupyter Lab here, it's a very basic Jupyter Lab. You have very few packages installed. And the flexibility in Galaxy is you can install whatever you want in your environment. So you have the full flexibility on any new tools or packages you would like to install to make to perform a new image analysis. So for instance, here I will install some package like Pooch for getting data from the Zenodo. I will use scikit-image and matplotlib, are very standard library in Python. So I can install them, for instance, with pip install. So I tried before, so it's a bit faster because sometimes it can take a bit of time, but you can always install any new packages. And then I will do exactly the same analysis as Leonid. This is to not to confuse everyone. So I'm getting data here from Zenodo, and this is the same b2.zip file, and it will download it locally. So I will have a folder, data folder here, and if I look at it, I can see that we have different TIFF files, similar to what Leonid showed before. Then I can select one file, as before. So usually when you prototype, you don't do an analysis on many different files, you go step by steps. So I can take one file, I can open one file, so I can use this SK image Python library, which is very common if you are a Python user. And then you can read your image. You can also get metadata as usual. So it's really like coding as you would do if you are a Python programmer. You can look at the data, and you can also visualize the data. Similarly to what Leonid was doing when we clicked on the visualize in the Galaxy. And in fact, everything you see in Galaxy, you always have code behind. And this is very transparent. You can always look at what has been done in the Galaxy tool. And you can also start from there, for instance, for improving the algorithm. So here I can make some visualization with EMShow, which is very basic visualization in Python. And similarly, we see some of the cell, but there is not so much contrast. So we can also do some normalization. And using the same algorithm as Leonid showed, we can import the skimage Python library, and we can do exactly the same kind of equalization. And then we can, again, visualize. So here I'm repeating. So it's like a Jupyter notebook. You are usually prototypes, so you can repeat the same thing again and again. But when I start thinking about how I could automate this process, I'm thinking, okay, if I visualize very often images, I can start writing a function. So I will define a function, and this function can later, for instance, be a tool in Galaxy. So here I will define the function that can visualize an image. So every time I take a raw image, I will do some normalization so I can see the different cells. And this is what I do here. So every time I want to visualize an image, now I will call this visualize function. I can also do some filtering, and here I can use any Python filtering function I want. So here it's a very simple one from SciPy. The same as you used, Leonid, and I can use the same filter with the same sigma value, but I could also experiment these different values. I will get a new image. And as before, if you want to visualize, this time I don't want to type everything manually. I can already start to think about future tools. So I will use a visualize function I defined. And it enables me to visualize the image quickly and see the contrast. I can also do some segmentation, and I can use different functions for the segmentation from skimage. And we are using the same Otsu filter function, which is very common. Even if this is not always very powerful, it works well on this kind of images. And again, I can visualize the segmented images. And this is very similar, or exactly similar to what Leonid did. So Leonid is like this implementation, operationalization of this kind of tools, where you prototype, then you think about how you could automate your workflow to write small tools that could be reused and create workflows that can make much more complex data analysis pipelines for not only you, but many other people. So here, again, we can do this labeling as Leonid did, where we can give a label, a value for each of the cell here, using this skimage measure label function. And again, I will run it as usual, and I can again use my visualize function. And similarly, so here we have exactly the same as you had, where it's not always very clear, but we have one color for each of them. And we can also make some overlay images using this skimage morphology as morph function. And here we define some additional images. If you remember at the very beginning, sorry for going back quickly. I wanted to show you the shape of the image here. The image is a 2D image, so it's not a square image, but nearly. So it's only one channel. It's a TIFF image. And with some function, sometimes you want to have an RGB image. So what you want to do, especially when you think about automating and making a function that is reusable by many other users, you want to make, for instance, a function that could take different types of images and will make this image usable for the next function. So for instance, here, what we will do is many of the functions need RGB image, but sometimes you don't have an RGB image. So what you do, like here, we have only one image, which is a 2D image. And what we are doing is copying the same in the R and G and B. So then you can use different algorithm. And this function here tries to take into account different types of images you would have and prepare them for like a segmentation contour analysis, like a RGB image. And again, if you think about a new algorithm, you maybe want at the beginning to write code without defining function, but as soon as you want to automate and make like a Galaxy tool, you will write a function that could be later on turned into a Galaxy tool. So here, for instance, we are defining a seg contour function with different parameters, and these parameters here, you can think about already how it would look like in Galaxy as a tool. The tool could be called, for instance, segmentation contour or whatever meaningful name, but at the same time, it will have these types of parameters. So in the Galaxy interface, you will have to pass an image, a label image, and then some parameters for customizing the plots, for instance. So if I define this function, I can apply it here. Oh, I forgot to execute this cell, which is what we have when we run Jupyter Notebook. So now I execute the cell, and then this function would run, and I specify I want to have a line width of 2. I want to have red for the contours, and the label will be yellow. And of course, it can take a bit of time. The image is not very big, but it still needs to be run. Should take not too long, hopefully. Yes. So now we have something which is very similar to what you had in the pipeline showed by Leonid, like a label with a number for each of the cell. And we took an image where it worked relatively well. And here you can see a bit like the different steps you would have to do, for instance, if you wanted to improve this workflow and this tool and create a new tool in Galaxy. But you can do many other things because, of course, it's fully flexible. And here you have the full Python ecosystem, and you can install any new packages. So, for instance, I wanted to show you here. I still have a bit of time, I hope. Yeah. So here I'm going back to one of the images we had at the beginning where we can see all the different cells. And I wanted to show you, for instance, we can save the image in a different format. So here I'm trying to use the OMISAR format. It's maybe not super relevant because this image is originally as a TIFF format, but this is to show you what we can do. So as a prototype, I can install new packages. And I can here, for instance, import the OMISAR function and the writer. So I will write the image into a ZAR. And why do I do that? It's because, for instance, when you go from a TIFF to a ZAR, ZAR is a cloud optimized data format. So I could put, for instance, on a cloud bucket to make it accessible to everyone. But I also can parallelize because here I have a small image, but when I want to run on a big not only on a large number of images, but on one big image, maybe I want to split the computation and to make it in parallel. So here, let's start to write first this simple image. So from a small TIFF here, I artificially create a ZAR file where I'm using this OMISAR. And because we have only one 2D image, I create only one level in the OMISAR. And in terms of chunks, so this is how you split your image. I take the full image because it's not very big. But I will show you that when we read the image, we can change the chunking and we can parallelize. So here I will, as a test, read the image, the new ZAR file, and I use another package which I installed, which is called XRA OME-NGFF. And I can open this ZAR file, and I can specify how many chunks, the size of the chunks, and I use this task array wrapper, which is also part of this package, and it will enable me to parallelize the computation later on. So as you can see here, I don't have one block of image. I have many small chunks, which means each chunk or each small cube or smaller cube here, I can run them in parallel. If I have several processors, it means it will speed up the computation, especially when you have complex image analysis. So here I do just some renaming of the values to have a variable which is called data. I can select using the selection, and I can plot, so very similarly to what we did earlier. And I can also make some interactive visualization, so it will take a bit of time. And when you have this chunking, these chunks, like the default plot with Matplotlib is very slow because it has to handle all the different chunks. Well, if I use HoloView, which is interactive visualization, it's another package in the Python ecosystem. I can make a visualization and I can make it interactive. So here, for instance, I can see each of the cell values, and I can also zoom in. So for instance, if I want to interact with a specific area and cell, I could zoom as much as I want, and it makes the process much more interactive. And I think that's all. And this image, you can also save it as an HTML and reuse it later on for another process. I think this is all I wanted to show you for this interactive part, which was very similar to what Leonid did, but in a more interactive way with the Jupyter Notebook. And I will stop sharing and give the floor to Ricardo.
So thank you, Anne. I will just start to share my screen. So you should be able to read my screen now. We talk a little bit about image processing with Galaxy in two different ways, and now we will go more a little bit in the direction of the data management. So I will show you, like, using Galaxy, how to do upload and fetching data into Omero, and also how you can fetch OMEZAR file from IDR and visualize them in Galaxy using the tool Visual Viewer. I don't know how many of you actually are used to Omero, so I have to just give you an overview for who doesn't know. So Omero, in a nutshell, really fast intro, is a macroscopy data management tool, and it's a pretty cool one because it allowed to share data, to annotate them, to structure it in a certain way that help you with your daily research data management tool with images. Just to give you this fast overview, so images have like unique ID, so you can really link a single images to a specific number. You have a specific tag system that allowed you to create a hierarchical structure of your data and have different tags for different images and search it in a nice way. You can attach also metadata that it work sometime with key value pairs that are also searchable. So you can search, for example, associated value like experimenter, instrument, biological entity, and so on. This is completely flexible and depend by your experimental setup. You can attach files, so table and attachment. This can be the result of your analysis. And also Omero support up to 140 different image formats type. Another huge nice thing is that it's integrated the visualization tool. So when you have your images in Omero, you can just simply click on the different images and visualize it on a web browser. So all these things together make it a powerful tool for research data management with images, and can become even more powerful using Galaxy, and I would like to show you. So I prepare a video for this specific demo just to stay in time, and I will just start it. Yeah, so for this demo, we will use the Omero intranet in the UFZ, so our Eastern UFZ, and we will use this dataset that is uploaded on Zenodo. So this is a subsample image from this specific publication from Nature. And as you can see, is just the image plus some tabular file with region of interest. I already upload them into Omero here on the right. And you can see that there are these images as a collection. And I also uploaded the tabular file with the different region of interest that you have like points described. And I upload also some metadata that I would like to associate to my image. So these are random thing, organism, and so on. I can search the tool, my Omero tool, because I want to upload these images. I can just put the image that I want to upload. So we can upload 92 and 94. And I can target a data set where I want to upload this image, for example, Galaxy Demo. And as Leonie showed, I can just start the tool. And on the right, the tool is XQ. So it's on gray, now it's yellow. So it means that it's starting. And now in the next step, this will be uploaded into Omero. So these are the different Omero tools that we have at the moment. Uploading is just taking some time for the connection to Omero. If you have more images, this will not take more time. And if we go back to the Omero instance of the UFZ, soon we will see that this upload. Just need some time. The tool is still running. And you can see here that the image were uploaded into Omero. So with Galaxy, I managed to upload it directly in the Omero Internet instance. What I can do now is to associate metadata. So I can select the dataset where the images are stored, selecting the object ID. This is the dataset. So okay, that's a specific number. And I can decide to associate key value pairs. So it's the metadata that I showed you before. I can give an annotation name, for example, Demo Galaxy, running the tool. And I just forget, for example, the output of the Omero image tool. So the one that we ran before, we have like the ID of the image there. So the one that were uploaded. The Omero metadata import works successfully. If you go back to Omero, you can see that here on the right, we have all the metadata. So the CSV file that is now associated to the dataset. As I said before, we can import also region of interest that can come out from analysis. And this I have just to select the tabular file with these rows. And again, I have to select the image ID where I want to associate this region of interest. And after this, I just run the tool. It's like Q again with the status gray. It will soon switch to yellow. It means that it's working. And as you can see now, if I open my image, and I go on the row, there are regions of interest that are associated to the image. And this is coming just from the tabular file that I uploaded before in Galaxy. The other image doesn't have it because we select just this one here. I want to show you how to do like some filtering. So if you have many images and you want to search it with specific input, for example, I want to search all the images that are in specific dataset. Again, I take the URL of the Omero and I do image ID, and I want to have all the ID of the dataset 4169. And these are two images inside. I can run the tool, Q again. And then when it's starting, it should spit out the ID of the image that are associated to this dataset. Starting. Take a bit of time. And here we are, we have the two ID of the image that are inside. If I want to do more fine grain, again, I need to put the Omero URL. This can be automatized in later step. And for example, I want to search for key value. And for this image, I will add some metadata, some key value. And here I can put the user, and for example, Ricardo. And I want to search by using this kind of association, user and Ricardo. So I can go to the Galaxy back, search for the key user and for the value Ricardo. And then I can do the list of images that I want to search for this key value pair. And I will put the two images that are inside this dataset. And if everything works correctly, just one ID will come out. So the one that have this key value pair association. You can imagine when you have a data set with thousands of images, this became really useful because you can just get the one that have a specific metadata associated. So it's run, and then you can see you have just one ID that is the one that have this key value pair. So all of this is pretty powerful again, because you can select a specific data set, and you can also download this image. For example, I want to download the one that have this key value pair associated I showed you before. So this is the ID that I can put inside, the one that I get from the tool Omero ID. And I can just run this one here. And it will download the image as a zip file. And this is nice because when you want to download many of them, then you will have like a zip file with many, many images that, again, you can reuse in Galaxy to perform other analysis, as Leonid showed before. So here it's done. And just to show it, I can just download it, open it, and I have my image back from Omero. So we did like Galaxy Omero. Then to show that this can be applied to a workflow, this is a nice workflow because you have three input, the images, the dataset, and the Omero server, and you have a huge step, the red one, that is just image processing. That is basically doing the step that Leonid showed before. And this workflow, it automatically upload the image in Omero, perform all analysis, and then upload the result into Omero directly. I have to put the images as input, the target dataset, and the Omero server address, and I just start it. And now it will just start the full workflow in one round. And this will take a bit of time, but not so long. And in the meanwhile, I will show you how to visualize OMEZAR using Galaxy. So as I said, there is an interactive tool that is visualization tool that is called Vizar. This allows to visualize OMEZAR file in Galaxy. And what you need to do is like to take, for example, a link from the public OMEZAR data. We can take this one for EDR 0077, copy it, and then we upload it by pastfetch remote data. Then we have to modify the deferred data resolution. And then we just start it. And it will slowly upload the data, not so slowly. It will take a bit of time. This is the Galaxy EU. In the meanwhile, we can check back our workflow is going. As you can see, it has like all the steps in green that are performed at the moment, while some are still running. Omero image import is running at the moment. It's performing some thresholding, splitting the file, some data wrangling. But you can see they are running fine, it's going through. These are the result of the thresholding, for example. So this was performed within the workflow. And we can go back also now to the workflow itself. No. Extracting the image feature. Yeah, this is again the workflow execution. And in the meanwhile, the ZAR file should be done. The images are here in the Omero, so they were uploaded. And if you go back to Galaxy EU, we can see that the ZAR file was uploaded, and we can see it directly on Galaxy. We can change the channel, so we can interactively act on the image, check for the different Z stack. So we can just play around with it, and we can do it with any of these images that have worked. Back on the workflow, we are in the last step of it. So everything was uploaded, the image processing analysis was performed, and the only thing to do now is to upload the metadata and the result that we're producing during the analysis. You can see the image here. And here, there are like parts value parameters. So the tool that is running at the moment is that just collecting image ID from Omero in order to associate the result to the correct image. And this is done. And the last two steps will be to import the region of interest and the metadata. Now it's running, and this will be complete quite fastly. Here, the ROI you can see are already there. So the region of interest are already start to be uploaded. And I want to underline that this was created in Galaxy. So this is not tabular file or anything that we're creating within the workflow. Everything is done. And you can see that you have also a file attachment. Okay, we have the image with the region of interest created in Galaxy. And then you have also an attachment with the result of the segmentation. Also, this created in Galaxy. So with mean intensity, perimetry, and axis. And yeah, as I say, this is really nice. You have everything in one. You put your image in Galaxy, and you process your image processing in Galaxy, and then transfer everything in a repository where you have the organization of your data in one go. And this is also pretty flexible according to your image necessity. And yeah, with this, I'm done, and just stop sharing my screen. And that's it.
Thank you, Ricardo. So we have now a couple of minutes for me to present a few things, and then we can take some questions. We will answer already some in chat, but we can still take some. So I'm sharing my slides again, and I will do now the full screen. Okay, so summary of everything that you've seen from the three of them. So that's Anne, Leonid, and Ricardo. I think you saw from different angles how you can do your image analysis there. And I wanted to highlight or summarize everything in one slide as different features that are available for you to use. So the first one, this is an open source platform. So that means that you can take the code, and you can reuse it, you can take the platform, install yourself in your institute, do as you like in your local computer, do what you want. You can also contribute to it if there is something that you would want to improve there. There is also open infrastructure. So you have now public servers, and that if you don't have the computational resources at your institute to run this analysis, you can use these public ones to use this. So it's open to everybody. You only need to have an account and a browser and an internet connection, and that's all you need. That means it's also accessible, and it's also having an user-friendly interface that you saw today in different examples. And it helps you to create this reproducible and transparent analysis. You could see how Leonid was assembling this step-by-step workflow, but then he could extract the whole thing as a single piece somehow. So this also helps with enabling the sharing of these resources in a very easy way. In terms of compute, there was some question in the Q&A box as well, and I was trying to answer this one. It depends on what you have behind the server. So we are now here talking about the public ones and what they offer for you. And that's CPU and GPU capabilities. In the backend, you can have maybe HPC cluster from your institute, or you can have your local computer, or you can have cloud resources. It depends on what you have. It's how the operations would be faster or less. And you don't need to deal with any of this. So this is totally transparent to the users. You don't need to know if there is cloud behind it or what it is. That doesn't matter. It's just the interface what you need to be concerned about. It's also scalable in the sense that you can also share in other nodes. So for example, there is a network of different servers that are connected. So if, for example, the data lives somewhere else, it could be that you submit the job in a server, but it gets computed somewhere else. That's also an interesting feature in terms of, for example, if there are no GPUs in one, but you need that, it could be derived to another one. So that's something that it's called the Pulsar network, and it's also offered by the Galaxy community. In terms of data management, you've seen from Ricardo many of these different things. I also wanted to mention the deferred data. And one of the questions in chat, there was something about the quote as well. So you have 250 gigabytes by default. You can increase that. You can ask for more. But with the deferred data, you can get big data sets directly to the compute node, and you don't need to consume that in your history. So that's also a nice feature to have there. There are pluggable data sources, so you can see that you can get the data directly from Homero, for example, but you can do this from the IDR. So you can get these data sources in a very easy way. You don't need to download this into your computer and then unload it again to another server or something like this. The export with provenance is also interesting because you keep track of everything that happened. So any other person would reproduce this, or your future self that we usually forget what we did a while ago. So that's also a nice resource for us. And the programmatic access I mentioned at the beginning as well. So there's an open API standard, so anyone can go there and with some commands run and start and stop the processes and so on. So those are the summary points, and now we have a couple of things on the future plan. So all of us here were showing bioimages, but not all of us are from bioimaging. So Anne, for example, is coming from the environmental science community. And when we exchange about these different image analysis things, we see that the needs are really not so different. So you can see here objects that are being segmented, right? And the top ones are trees, but then there is a river, but there is garlic, then there's cells. So we don't really care so much about what is in there, but much more about the task that we need to solve, right? So we want to expand and work with other communities on this. And for that, we have a project that starts in March that is called Fair Image Analysis Across Scientists, in which people from environmental sciences, from astronomy, and from bioimaging, we come together and following these different fair practices and to repositories and ontologies and so on. We want to make this homogeneous in a way that the same image analysis workflow in Galaxy could be done regardless of the input. So if I put cells, it should run and detect the cells. But if someone else puts like a galaxy or stars like this, it will also detect the stars. So that's what we are going to work on this project. It's going to last for a couple of years, and it's going to start very soon. Yeah, so if you want to join us, if you want to ask questions, if you want to participate in the discussions, we are meeting every third Wednesday of the month at 4 p.m. Central European times or summertime. And we have also a public calendar. I will share the link to the slide so that you have all these details in the chat. So we have a public calendar with all these things and all the different events that we organize. And we have different, the spring tour is coming up, and we have several talks and different events. And one of them is the Imaging Image Data Community Days. That's a whole week event. It's all online. Registration is now open, and we will have a session there for this group of people that are gathering around the Imaging expert group on fair image data workflows. Then we're organizing a hackathon in Freiburg, and it's about image analysis Galaxy. It's also hybrid. So if anyone wants to contribute with, for example, a use case or something that you would like to see in Galaxy, that's something that we are always looking for. So in the meetings, if you want to join and say, okay, this is what I do, and I don't know how to automate this, maybe we can give you input or help you create this automated workflow. And in May, there is also a big event that Galaxy is organizing for the last year with thousands of attendees. There's the Galaxy Training Academy, and there's a whole week event with the recordings on different sciences. So you, as a trainee, you record a tutorial, and you also provide a tutorial, and then people join and follow these instructions. And then in that week, the trainers are available in chat to reply to this question. So we are aiming also to participate to this one. And finally, an in-person one in the US that is going to be GBCC. This is together with the bioconductor community. It's going to be end of June in Long Island, and registration is also open. So that's for the events that we have. Here are our emails. Here are all the projects in which we're involved, our institutes. We also have a Matrix channel in which we exchange plenty of things. So if you're interested and want to create an account there and join the chat, this is totally open for anyone to join. We have a couple of pages in the Euroimaging website in the expert group for image data workflows. And then we have also another page as a community of practice for image analysis in the Galaxy Community Hub. And I think that's all we had, but I last minute added this slide for the webinars that are starting tomorrow. This is the AI for Life one, so I hope I will see many of you here as well. The first one is by Anna Kreshuk and Wei Yang on AI for Life. What can it do for you and your images? So if you're interested, you can still register. And I think that's all we had for you. I don't know how we're done with time. We have a few minutes. So happy to take questions.
Thanks, everyone. That was Great, very intense. And I think we had a number of questions, but as far as I see, maybe there's one left. Okay. So shall I read it out? So Ryan is asking, how easy is it to combine different data types within a workflow, e.g. images, point clouds, surface meshes, graphs, etc.? Is it only limited by the available tools, or are there constraints on the data types?
Does anyone want to take this? No, I can take it. Okay, so you can combine whatever you want, right? So you saw that Leonid was combining the mask and then the overlay, and then this is in terms of images, but you could also say, same as we show all the different image analysis tools that you can chain into a workflow, you can also add some other data types. It's important that the data type is part of Galaxy, so it's like an accepted data type. It cannot be like a totally random thing, new format that someone created that is very strange and nobody knows. So it has to be added first to the platform so that it's recognized somehow. But besides that, you can combine in the workflow whatever you want.
Okay, there's another one. We have a few minutes left, so maybe we can try. So someone is asking, can I export Galaxy workflows to other workflow engines such as Nextflow? For example, if I want to scale up my workflow on a platform such as a university local compute cluster, where Galaxy is not available.
Anyone wants to answer? Should I take it? Okay, I take it. No, I mean, yes and no. So there is this, there was some work lately on CWL that you can have like a standard way of representing this. And in principle, that would enable different workflow managers to export in a format that is common to all of them. However, as far as I know, this is the last that I know. If anyone knows better, please correct me here. There are many specific parameters that are specific of particular workflow managers. So that means that it may not run in a different way, in a different system, right? So you can export and you can read in a different format, but that doesn't mean that you will run it and you will have exactly the same thing.
So maybe I can just add, Bea. So I
Yes,
do
please.
it very often, this where, because as I said, all the tools, they are publicly available, the code. And usually you can extract and you can even see like the command line. So it's fairly easy to build a single transformer for like a Galaxy workflow to any of your SnakeMake or whatever you are using. So we do it quite often. But we don't have very complex maybe workflows, but or like many tasks. But it is feasible.
Okay, great. That brings us to the end. I think time is nearly up anyway. So thanks everyone for attending and to the presenters for a great job. Beatrix, if I understood this correctly, you plan to have an image SC follow-up thread as well.
Yes,
Yeah.
I don't know if I need to create a thread or something, but happy to discuss there, yes.
Yeah, so we will look at this. So whoever wants to follow up this discussion, you can do it then on ImageSC. We will post links to that in our social media channels so you can find it easily. Okay, then everybody a great rest of the day wherever you are, and maybe see you next time. Thank you.
Thank you. Bye-bye.
Bye.
Ciao.